If you're watching how fast AI is moving, the goalposts have definitely shifted.
Mhm.
It's not just about getting one LLM to do one thing anymore. The real challenge, maybe the real headache, is getting these AI agents to actually work together like a real team
Mhm.
on complex stuff. But there's this huge hurdle.
Information asymmetry.
Exactly. Information asymmetry.
Yeah, like the fundamental problem in almost any collaboration, right? People, or in this case agents, just know different things. If I know part A and you know part B, we can't solve the whole puzzle unless we talk.
Right. We have to figure out what the other knows and bridge that gap.
We have to coordinate.
Okay, so let's unpack this. We've been looking at some really fascinating research that digs right into this problem.
Yeah, the goal wasn't just, can LLMs talk to each other? It was about how well they cooperate when they have to rely on each other because they don't have all the info.
So how did they set that up? What was the experiment?
They created this really clever setup based on a classic logic puzzle. Think of it like a tabletop game, maybe the Einstein puzzle, adapted a bit.
Uh-huh.
You have two LLM agents, partners basically, and their job is to put objects like, say, a teddy bear, a ball, a toy dinosaur into the right bins on a grid.
Agree. Okay, so spatial reasoning is involved. What kind of rules dictated where things go?
They were all spatial relational constraints. Things like the bear and the dinosaur have to be in the same row, or maybe the ball can't be in the same column as the bear.
Got it. Standard logic puzzle stuff.
Exactly. And the agents had to satisfy all these rules together to find the one single correct layout.
But, okay, if both agents knew all the rules, that wouldn't really test collaboration, would it? This is where the asymmetry kicks in.
Precisely. That's the core mechanism. They took the full set of rules needed, let's call it C, and they split it. They split it into two minimal sets, C1 and C2, with no overlap. Agent 1 only got C1, Agent 2 only got C2.
So neither agent could possibly solve it alone. They had to share information.
Absolutely mandated. They had to communicate to figure out the final answer.
That's a really neat way to force the issue. So how did they measure the quality of that forced communication? Did they test different ways the agents could talk?
They did. They looked at 4 different communication setups, or what they called action-based configurations.
Okay, what were they?
So first was information providing only. An agent could share rules it knew, just broadcast them, but couldn't ask its partner anything.
Just talking, no listening for requests.
Right. Second was the opposite, information seeking only. The agent could only ask specific questions like, where is the bear?
Yeah.
But couldn't volunteer information.
Okay, only asking.
Third, information providing and seeking. Full communication, share what you know, ask what you don't, bidirectional.
The works?
And the fourth, the control condition, really. No information exchange. Agents could only move objects or pass their turn. Total silence.
Operating blind, basically. Okay, so you have these 4 modes. How did they judge performance? It wasn't just, did they solve it?
Yeah.
Right. You mentioned efficiency.
Yeah, efficiency was key. They used a metric called the step ratio. And we should probably explain that because it really frames the results.
Definitely. What is the step ratio measuring?
It's simple but powerful. It's the total number of actions the agents took divided by the minimum possible actions needed for a perfect solution.
Total actions divided by optimal actions.
Yep.
Got it.
And here's the kicker. Every single action counted. Moving a toy, that's one step. Passing your turn, that's a step.
Okay.
But crucially, asking a question was a step. And sharing a piece of information was also a step.
Whoa, okay, so talking costs just as much as moving. That really puts the pressure on concise communication.
Exactly. You can't just ramble. Sharing stuff the other agent already knows or asking vague questions, that kills your step ratio. You want the lowest ratio possible.
It forces them to be smart about what they say and when.
Precisely. Get to the point.
Okay, so with efficiency being that critical, which communication style came out on top?
Well, probably not too surprisingly. The information providing and seeking set up the full two-way communication consistently got the best results.
Highest success rate, lowest step ratio.
Yeah, highest success, lowest steps. Having all the tools, being able to ask and tell, that was the most effective way to coordinate efficiently when information was split.
Makes intuitive sense. But you mentioned nuance earlier. What happened when you looked at the one-way streets? Providing only versus seeking only.
Ah, yes. This is where it gets really interesting. My first thought might have been, okay, just sharing everything you know, providing only should be pretty good, right? Just dump the knowledge.
Yeah, get it all out there.
But actually, no. The agents using seeking only, the ones just asking targeted questions, were significantly more successful and efficient than the ones just providing information blindly.
Really? Why would just asking be better than just telling?
Redundancy, massive redundancy. The providing only agents were like, that colleague who forwards you a giant email chain hoping the answer you need is buried somewhere inside.
Huh. Okay, I know that colic.
Right. The researchers actually quantified it. In some early tests, almost 80%, 79.35% to be exact, of the information shared by the providing only agents was redundant.
Wow, 80% waste. So they were just
What?
burning steps, telling their partner things the partner already knew or didn't need right then.
Exactly that. Wasted steps, increased noise. The seeking only agent, though, acted more strategically. It figures out, okay, I'm stuck because I don't know where the dinosaur goes relative to the bear. And it asks just that one specific question. It targets the missing piece. Much cleaner, fewer wasted steps.
That's a huge insight for designing these things. Don't just build data fire hoses, build agents that can ask smart questions.
Absolutely. Targeted inquiry beats blind broadcasting.
Okay, we have to talk about the silent agents, the no information exchange group. You said some models, llama variants, actually did surprisingly well, like over 81% success without talking. How is that even possible in a puzzle that requires information sharing?
Yeah, that was definitely a head scratcher at first glance. And this finding is really the pivot point where the conversation shifts from just efficiency to safety and true understanding.
Right?
When the researchers dug into why these agents were succeeding silently, they found it wasn't some hidden genius for deduction.
They weren't secretly figuring out the rules.
No, they weren't mastering the rules at all. They were mastering the game board, the physical environment.
So they weren't reasoning about the constraints. They were just learning patterns of movement, like watching the pieces, not reading the instructions.
Exactly like that. Without communication to worry about, these specific llama models seem to default to just learning the physical moves available and critically memorizing common sequences or patterns of how things moved.
Like rote memorization of transitions they saw during training.
Kind of. They were essentially guessing the next likely state based on learned movement structures, not based on the actual logical rules, the C1 and C2 constraints of that specific puzzle instance.
That sounds brittle. Like it would break easily if you changed the setup even slightly.
Incredibly brittle. Change the grid size, add a new object type, and those memorized patterns become useless. The agent would likely fail completely, that high success rate. It's a dangerous illusion of competence.
Right. It looks good on the test, but it hasn't actually learned the underlying logic.
And that points to a massive safety risk, doesn't it? If you have an agent achieving high scores, but it doesn't really understand the rules, just guessing patterns. Well, deploying that in the real world for something important, logistics, medicine.
Yeah, that's a recipe for disaster when it encounters something new. Generalization would be terrible.
Precisely. Success without understanding is a huge red flag.
Okay, so this discovery that high performance can hide deep flaws led the researchers to propose a solution, right? Something called the environment-based verifier. An insightful guardian, you called it. What's novel about this verifier?
What's really neat is that it's lightweight. It doesn't require massive retraining or anything like that.
Oh, interesting. So it's not another giant model.
Yeah. No, it uses feedback that's kind of naturally available from the environment itself. Like how a person playing a logic puzzle might double-check their steps against the rules.
So instead of trusting the LLM's internal, maybe flawed reasoning, it uses some external checks. How does the core part, the reasoning verifier, actually work? How does it enforce real understanding?
Okay, so simple checks might just see if one rule is met, like is A in the same row as B, yes or no.
Right.
The smart part of this reasoning verifier is it uses something called constraint transitivity. It builds a kind of logical graph.
Constraint transitivity. Let's break that down.
Sure. Imagine you have three objects, A, B, and C. The agent knows rule 1. A and B must be in the same row. And it knows rule 2. B and C must be in the same row.
Okay.
The verifier can automatically infer, using transitivity, that A and C must also be in the same row, even if that wasn't an explicit rule given to the agent.
Ah, like the transitive property in math. AB and BC, therefore AC.
Exactly. It builds out all these logical connections. So if an agent, maybe one of those guessing llama agents, tries to make a move that puts A and C in different rows.
Even if that move doesn't directly violate the rules it knows, C1 or C2.
Right. The verifier flags it. It says, hold on. That move breaks the overall logical consistency When you account for these inferred relationships, it forces the agent away from just pattern matching towards actual logical deduction.
So it acts like a constant logic checker, looking at the whole picture, including the implied rules.
Yeah, like an external tutor saying, think about the downstream consequences of that move.
That sounds really powerful. What kind of impact did adding this verifier have on performance?
The impact was huge, really significant gains in success rate across the board.
For all models, all
Yeah.
communication types.
Yep, absolute increases in success rate ranging from about 10% on the low end up to 40% in some cases. It just cleaned up a lot of errors.
40%, wow. And presumably it specifically helped with that dangerous guessing behavior.
That's the key link. When they analyzed the types of errors, the verifier drastically reduced the ones categorized as wrong rule understanding.
So it directly tackled the core problem.
Exactly. It really pushed the agents, even the ones with full communication, to actually comprehend the rules properly. This leads to much safer, more interpretable AI collaboration. You know why it's succeeding.
Okay, that covers the agent-to-agent interaction and the verifier. But you mentioned there was a human element too. They tested these agents with people.
They did. They paired the different agent configurations with human participants trying to solve the same puzzle.
And how did the humans do?
Humans, unsurprisingly perhaps, nailed it. 100% success rate working with any of the agent types. We're pretty good at logic puzzles and collaboration when we need to be.
Okay, good for us. But what did the humans think of their AI partners? Was there a preference?
Yes, and this is where we see a really interesting misalignment. Efficiency didn't equal preference. Well, objectively, the agents with communication capabilities were more efficient. Remember the step ratios. The best agent, providing and seeking, had a ratio around 1.39x optimal. The silent no exchange agent was much worse, like 1.86x.
So the communicating agents took fewer steps overall.
Right. But humans didn't necessarily prefer the absolute most efficient partner. They strongly favored the agents that were proactive.
Proactive, meaning the ones that shared information without being asked.
Exactly. The information providing and seeking agent was liked, but so was the providing only agent, even though the latter could be redundant.
Okay, so they liked the talkers. Why did they dislike the seeking only agent, the one that was efficient but only asked questions, and the silent one?
The qualitative feedback was really clear. The humans felt confused by the agents that stayed quiet and less prompted or were entirely silent. Think about the seeking-only agent. It might be very efficient, only asking for exactly what it needs. But from the human's perspective, it's just sitting there. The human doesn't know what it knows, what it's thinking, why it's not doing anything.
Yeah, you'd constantly be wondering, do they have a piece I need? Should I ask them something? What's going on? It puts the cognitive load on the human.
Precisely. It's like working with a colleague who never gives updates. You can get the job done by constantly poking them for info, but it's frustrating. You prefer the one who says, okay, I finished part A, now I'm starting part B. Do you need anything from A?
Even if that update takes an extra step or two in terms of pure turn economy.
Right. The human preference wasn't just about minimizing steps. It was about clarity, initiative, and feeling like you had a real teammate who was actively participating and keeping you in the loop. Trust and understanding were key.
So being a hyper-efficient black box isn't actually ideal for human-AI teaming.
Seems not. Transparency and proactivity seem crucial for building that trust, even if it costs a tiny bit of theoretical efficiency.
Okay, so let's try and synthesize this. We've gone from basic LLMs to collaborating agents facing information asymmetry. What are the big takeaways here?
I think there are two really crucial insights for anyone thinking about building or using these systems. First, aligned bidirectional communication, being able to both provide and seek information, seems optimal for LLM teams, not just for getting the job done, but doing it efficiently.
Ask and tell is better than just one or the other.
Right. And second, maybe even more importantly, we need ways to ensure these agents are actually understanding the rules, not just pattern matching or guessing. Things like that lightweight, environment-based verifier are critical for safety and interpretability.
To prevent that dangerous illusion of competence.
Exactly.
So for you listening, as you're designing or maybe interacting with AI collaborators in the future, what's the practical advice?
Well, this research strongly suggests you need to think beyond just task success or raw speed. Prioritize communication protocols that feel transparent and proactive.
Build an agent that acts like a helpful colleague, not just a silent tool.
Yeah, aim for an AI teammate that makes its reasoning and status clear, rather than an opaque box that somehow spits out the right answer, sometimes.
Because if we just optimize for speed, for the lowest step ratio above all else,
We risk building systems that are incredibly fast and efficient, but leave their human partners feeling confused, out of the loop, and ultimately distrustful.
Which leads to a final thought, maybe. Does maximizing pure algorithmic efficiency sometimes come at the direct cost of human usability and the feeling of genuine collaboration? That tension between machine optimization and human trust, that's something important to keep in mind.